Okay, I'm going to talk about closed systems and measuring chemical energy. So what we want to do when we're going to try and measure the chemical energy involved in a reaction is we want to use a closed system. So the idea here is if we imagine some sort of perfect system like this, where we have some substance that represents the surroundings. Maybe it's full of water. And that represents the surroundings. And then we have the chemical reaction going on down here. Some chemical plus some other chemical is going to go and make some chemical like this, plus a whole lot of energy. And then the idea is when that energy is released, it goes into the surroundings. We say it's closed if none of that energy leaks out into the rest of the world. To do that, we could imagine taking this system and completely isolating it from the outside world. So this would maybe be like a vacuum or something. But even with a vacuum, heat can radiate out of the system. So really, no matter how hard we try, we can't isolate systems. Completely. So an isolated system, the perfect example of a closed system, just doesn't exist. So what we try to do when we're making these measurements is we try to make the measurement in as isolated a situation as we can. A vacuum, kind of like your thermos that you might bring to school if you had hot soup inside, is pretty good. The radiation that leaks heat is a relatively slow form of energy transfer. So this is the main best way we do this. But we can do this in cheaper and not quite as reliable ways as well. We can use things like a styrofoam cup. And because styrofoam doesn't transfer heat very quickly, if we put a lid on this cup and we have our water in here and our chemicals in here, then hopefully all of the energy, very little energy, is being exchanged with the outside world. This device, where we try to keep it as isolated or closed from the outside world, is called a calorimeter. I should have looked up how to spell this first. Something like that. And this type of measurement is called calorimetry. The old unit for chemical energy being the calorie. So calorimeter, calorimetry, where we measure it. So the idea here is if we have a completely closed or isolated system, and again, remember that never really happens, so this is a source of error in all of our experiments. But if we had that, then what we could assume is that the energy change for the reactants would be equal to the resulting energy change for the surroundings. The only difference being if the reactants gain or lose energy, the surroundings will do the opposite. So if the reactants have to take energy from the surroundings, then the surroundings are going to decrease in energy. Or alternatively, if the reaction produces energy, if the reactants go to a lower state of energy, that energy is available. So these two numbers are opposite to each other. So the energy total is equal to negative Q. That's if it's a closed system. The truth is, this is always going to be a little different from this because this is going to be a result of interacting not only with the chemicals but with the rest of the world. Ignoring that, for our calculation purposes, we'll pretend that this is perfectly true. So the idea here is that if I know the mass of my water and I know the specific heat capacity of my water, which is well known now, and I can measure my temperature change, so I have to put a thermometer in here, so I can see the temperature go from here to here and get my delta T. Then, and I know my amount of reactants, N, and I know my delta H, I don't know my delta H. If I know M, C, delta T, and N, I can measure my delta H from my reaction. So let's just imagine. So we have some system. And in the system, we're isolating it, so this is a vacuum from the rest of the world. And here we're going to have a compartment where the reaction is going to happen. So here we're going to say take some methane and burn it in some air. And that is going to be like the natural gas reaction that happens in your furnace, and that's going to produce a bunch of energy. And then we have a separate vessel up here with some water in it, and we know we have, say, some amount of water, I don't know, let's say 500 grams or something. And we know the specific heat capacity of water is going to be 4.18 degrees Celsius per gram per MC delta T. Sorry, joules per degree Celsius per gram. And so we have a thermometer sitting in here that we can see for some reason. So here's our thermometer, and we see the temperature go from, say, 20 degrees to 40 degrees. And we know how much CH4 we burned, so we know our number of moles. Let's just make it, I don't know, 1 or something, it doesn't matter. Then I can say that since this is isolated, or since it's closed, then all of the energy that was produced by this reaction is going to go into the surroundings. However, if these guys are going to a lower energy state, as in an exothermic reaction, that is going to release energy to the environment. So if these guys go down, this one goes up, or vice versa, right? Because whatever this is losing, in this case, this is gaining. So with that in hand, I could do N delta H would be equal to MC delta T. And I could take my delta T, and my M, and my C, and my N, and insert them all into the equation, and all I'd be left to find is my delta H associated with my reaction. So that's the basic idea of calorimetry. That's how we came up with all of these delta H values in the first place, by doing experiments like this, where we're very, very careful to keep our system as closed as possible. We're aware that in the real world, all systems, especially the ones we're going to work with in class, are really open systems. Energy is really exchanged with the environment. And this is probably our biggest source of error when doing calorimetry experiments. So that's what a closed system is, and that's how we use a closed system to try and figure out what delta H's are, or to do experiments with thermal energy.